Okay, so another question using Thevenin's theorem, right? In this case, we have two sources inside the Thevenin's box. So we are given this circuit and we need to calculate the voltage across 5 ohms resistor and the current through 5 ohm resistor. So we can treat the blue part as the part that we're going to apply Thevenin's theorem on, right? So in order to find, so we're going to effectively replace the blue box with just a Thevenin voltage in series with a Thevenin resistor. So perhaps I can draw it out, right? So we're effectively trying to replace the blue box with just a Thevenin voltage, VTH, and a Thevenin resistor, RTH, right? And then this is going to be your A and B. And from the perspective of an external load, right, it's going to see, it's not going to know that you replaced it. So how do we calculate Thevenin voltage, and how do we calculate the Thevenin resistance? We use Thevenin's theorem. So to apply Thevenin's theorem, right, the first step we're going to do is we're going to disconnect the load. So step 1, to find VTH, right, disconnect the load. So what this means is that we can redraw the circuit. So you have 24 volts here, 1 ohm. Here you have 2 ohms on the top, 0.6 ohms, and 6 volts like this. And yeah, so, and then this is 0.5 ohms, and it connects to A, and the other one connects to B. But then now we've removed the 5 ohm load. So we remove the load, right, and isolate the blue box. So now we calculate the Thevenin voltage is going to equal to the voltage between A and B. So now we pretend that this circuit is like this, and we measure the voltage between A and B. So how do we find the voltage between A and B? We need to find the current flowing through this loop. So it's of interest to find this current, the current flowing through this loop, because if we can, then we can find the PD across A and B. So we realize that the 0.5 ohms resistor is not relevant because it's basically not connected. So as far as we know, right, we can actually remove the 0.5 ohm resistor because zero current flows through it. So yeah, maybe I just make it clearer. So the current flowing through the 0.5 ohm resistor is 0, right? So the voltage across it, right, is also 0. Okay, so we just restricted to this loop then. So okay, so how much current is flowing through the circuit? So much current flows flowing through the circuit is I. So I, right, is going to equals to what's the net the algebraic sum of the voltage sources is 24 minus 6 volts because they are opposing each other. Then what's the total resistance? It's going to be 1 plus 2 plus 0.6. So that's going to give us, right, punching into the calculator, we get that this is 5 ampere. So now we know that the PD across the 0.6 ohms resistor is going to be 5 ampere times 0.6 ohms equals to 3 volts, right? So with the polarity being this, because the current is flowing from positive to negative. So if this is plus 3 and this is, if the top and the bottom has a difference of 3 volts, right, then that will mean that the PD across A and B, right, now we can calculate it to be the PD across this 6 volt resistor. Sorry, what am I saying? It's the PD across this 0.6 ohm resistor plus the PD across this voltage source. So it's going to be 3 volts, right, from here plus 6 volts from here. And that's going to give us a total of 9 volts. So the Thevenin voltage is hence 9 volts. So now we know the Thevenin voltage is 9 volts. Okay, so now to find Thevenin resistance, right, we remove the load once again, and we remove all the voltage sources. So we remove all the sources and replace them with short circuits. So for Thevenin's theorem, right, if it's a voltage source, then we replace it with a short circuit. But if it's a current source, then we replace it with an open circuit. But in this case, we both have it's both voltage sources. So let's replace it with short circuits. So we're going to redraw the circuit. So there's going to be 1 ohm, 2 ohm here, 0.6 ohm. And now the voltage sources have disappeared, and we replace them with a short circuit. And lastly, we have 0.5 ohms like this, and A and B like that. Okay. Okay, so now by Thevenin's theorem, right, the Thevenin resistance is equals to the effective resistance between A and B. So what's that? That's going to be, right? So now we just do our effective resistance calculation. So we know that these two gives us 3 ohms, right? And then we have 3 ohms. So we take the 3 ohms and parallel it with the 0.6 over here, there's going to be 1 over 1 over 3 plus 1 over 0.6 goes to 1 over 2. So 0.5 ohms, right? And then we have a 0.5 ohms in series with 0.5 ohms. So 0.5 ohms plus 0.5 ohms is going to give us 1 ohm. So it's 1 ohm. So the Thevenin resistance is 1 ohm. And with that, we have enough information to solve the question. So now, all that's left to do is to find the current through the 5 ohm. It's just taking 9 volts divided by the total resistance, which is 6 ohms, right? So 5 plus 1 gives you 6 ohms, and that gives you 1.5 amps. Then for the voltage across the 5 ohm resistor, you just take 1.5 amps times 5, and that gives you 7.5 volts. And that is the answer.